Our next corrective measure involves transfer learning, that is, using pre-trained models like the BERT to come up with a more sophisticated question answering model. Let's now look at this paper on the BERT entitled Pre-training of Deep Bidirectional Transformers for Language Understanding. This paper is by Jacob Devlin, Ming Wei Shan, Kenton Lee, and Christina Tutanova of Google AI Language. They introduce a new language representation model called BERT, which stands for Bidirectional Encoder Representations from Transformers. The BERT is designed to pre-train deep bidirectional representations from unlabeled text by generally conditioning on both the left and right context in all layers. As a result, the pre-trained BERT model can be fine-tuned with just one additional output layer to create state-of-art models for a wide range of tasks, like the question answering task on which we're working on now, and language inference without substantial task-specific architecture modifications. The BERT is conceptually simple and empirically powerful. It obtains new state-of-the-art results on 11 natural language processing tasks. We see here that for the Squirt version 2 on which we're working on, it has an F1 for the test of 83.1%. The authors argue that current techniques restrict the power of the pre-trained representations, especially for the fine-tuning approaches. The major limitation is that the standard language models are unidirectional, and this limits the choice of architectures that can be used during pre-training. For example, in OpenAI's GPT, the authors use a left-to-right architecture where every token can only attend to previous tokens in the self-attention layers of the transformer. Such restrictions are suboptimal for sentence-level tasks and could be very harmful when applying fine-tuning based approaches to token-level tasks such as question answering, where it is crucial to incorporate context from both directions. Now recall that from the transformer model in the multi-head attention, we have this kind of attention weights, whereas for the masked multi-head attention, the attention weights are modified such that we are ensuring that every word only attends to itself and its past, and that's why we have this deep, for example, has here only attending to itself, and all the future words are not considered. So this is the kind of multi-head attention model used by unidirectional language models, whereas for a bidirectional language model, there is no masking. So if we have this word, for example, is, it attends to its past and also its future. And this turns out to work well for the text we are working with now, which is that of question answering, where the context or each word in the context is related to some words in the past and also some words in the future. So it's important to make sure that the attention scheme is bidirectional. And so we end up with this kind of attention weights instead of this kind of masked attention weights. BERT alleviates the previous mentioned unidirectionality constraint by using a masked language model as the pre-training objective. And this was inspired by the closed task. The contributions of this paper are as follows. They demonstrate the importance of bidirectional pre-training for language representations. Unlike the Radford et al. Paper, which uses unidirectional language models for pre-training, BERT used masked language models to enable pre-trained deep directional or rather deep bidirectional representations. This is also in contrast to Peters et al., which uses a shallow concatenation of the independently trained left to right and right to left language models. They also show that pre-trained representations reduce the need for many heavily engineered task-specific architectures, which is actually very important because BERT now can be used to come up with state-of-the-art performance on a large suite of sentence level and token level tasks, outperforming many task-specific architectures. BERT advances the state-of-the-art for 11 NLP tasks, and including that of question answering. In this section, the authors introduce BERT and its detailed implementation. There are two steps in this framework, that's pre-training and fine-tuning. During pre-training, the model is trained on unlabeled data over different pre-training tasks. And then for fine-tuning, the BERT model is first initialized with the pre-trained parameters. And then all of the parameters are fine-tuned using labeled data from the downstream tasks. And each downstream task, like the question answering we're working with now, has separate fine-tuned models, even though they are initialized with the same pre-trained parameters. The question answering example in figure 1 will serve as a running example for this section. Here we see how we do the pre-training of a BERT model, and now it is used in this different downstream tasks. Specifically for our question answering, we have our square data set where our aim is to get the start and end words in our context based on an input question. Now, as we've seen already, a distinctive feature of the BERT is its unified architecture across different tasks. Hence, there is minimal difference between the pre-trained architecture and the final downstream architecture. Let's look at the BERT's model architecture. The BERT's model architecture is a multi-layer bidirectional transformer, so this is without causal masking, and this transformer encoder based on the original implementation described in the Attention is All You Need paper, so it's kind of like what we've seen already. Now in this work, they denote the number of layers, that is the number of transformer blocks as L, the hidden size as H, and the number of self-attention heads as A. We've seen this already. For the BERT base, L equals 12, H equals 768, A equals 12. And the total number of parameters is 110 million. While for the BERT large, L equals 24, H equals 1024, A equals 16, total number of parameters 340 million. This BERT base was chosen to have the same model size as the OpenAI GPT for comparison purposes. Now, however, the BERT transformer uses bidirectional self-attention, while the GPT transformer uses constrained self-attention, where every token can only attend to context to its left. Let's now look at the way BERT has the input-output representations taken care of. To make BERT handle a variety of downstream tasks, the output, or rather the input representation, is able to unambiguously represent both a single sentence and a pair of sentences. For example, in the question answer task. Now for a single sentence, we may have machine translation task, we may have a classification task, but all these tasks are taken care of as BERT takes in one token sequence. Now, throughout this work, a sentence can be arbitrary span of contiguous text rather than an actual linguistic sentence. A sequence refers to an input token sequence to BERT, which may be in a single sentence or two sentences packed together. Now, they use the word piece embeddings with a 30,000 token vocabulary. And the first token of every sequence is always a spatial classification token, CLS. The final hidden state corresponding to this token is used as the aggregate sequence representation for classification tasks. Sentence pairs are packed together into a single sequence. We differentiate those sentences in two ways. First, we separate them with a spatial token, SAP, that's SEP. Second, we add a learned embedding to every token, indicating whether it belongs to sentence A or sentence B. So if we consider this input where we have two different sentences, the first one, my dog is cute, the other one, he likes play in. Now notice that we've added the CLS at the beginning, and then for this first sentence right here, we have this separation between this first sentence and the next sentence, he likes play in. And then after this, we also have the separation. So what the others did, apart from just putting this separation here between two different sentences is by including a segment embedding right here. Now note that we've been used to working with the token embeddings and the position embeddings right here. So now apart from this embeddings, that's the classic embeddings and the position embeddings, we have this segment embeddings where the words which belong to the first or to sentence A have this embeddings EA, as you can see here, and then these words which belong to sentence B have this embeddings EB. The BERT is pre-trained using two unsupervised tags. Here we have the tags 1, which is the masked language model, and tags 2, the next sentence prediction. Let's look at the masked language model. Intuitively, it is reasonable to believe that a deep bidirectional model is strictly more powerful than either a left-to-right model or the shallow concatenation of a left-to-right and a right-to-left model. Unfortunately, standard conditional language models can only be trained left-to-right or right-to-left, since bidirectional conditioning would allow each word to indirectly see itself, and the model could trivially predict the target word in a multi-layered context. Hence, in order to train a deep bidirectional representation, we simply mask some percentage of the input tokens at random, and then predict those masked tokens. This is referred to as a masked language model or the closed task. In this case, the final hidden vectors corresponding to the masked tokens are fed into an output softmax over the vocabulary to predict exactly which word it is. And this is as in the standard language model. And in the experiments carried out, the others masked 15% of all the word piece tokens in each sequence at random. It should also be noted that for prediction, we only do that with the masked words instead of trying to predict the entire input. So what goes on here is, if we have this as input, we now masked out 15% of this input and then try to predict those masked out inputs instead of predicting the whole input. Now, although this allows us to obtain a bidirectional pre-trained model, a downside is that we are creating a mismatch between pre-training and fine-tuning, since the mask token does not appear during fine-tuning. To mitigate this, we do not always replace the masked word with an actual mask token. The training data generator chooses 15% of the token positions at random for prediction. If the I token is chosen, we replace the I token with the mask 80% of the time, and 10% of the time we select a random word and a random token in the vocabulary, and the other 10% that token is unchanged. So if we take this example right here, we have this input sentence, my dog is hairy. 80% of the time we have to use the mask, and then 10% of the time we actually select a random word in a vocabulary, like say apple. So my dog is hairy turns to my dog is apple. Then 10% of the time the word hairy is maintained, and the purpose of doing this is to bias the representation towards the actual observed word. Now, the advantage of doing this instead of just always saying taking our 15% and then setting it to mask is that this doesn't allow the transformer encoder to lose its distributional contextual representation of every input token. Also note that we have this random replacement, which may be seen as a harm to the model's language understanding capabilities. And nonetheless, this is only 1.5% of all the tokens, since if we take 10% out of the 15% of all the tokens, then we'll obtain 1.5%. The 15% are the random chosen tokens which we want to mask, and then the 10% comes from this, where we select a random word or a random token in the vocabulary. Although these masked language models do not converge as fast as the left to right models, we prefer using them since the improvements we get from using them outweighs the training cost. Now we look at the second task, that's the next sentence prediction. It should be noted that many important downstream tasks such as question answering and natural language inference are based on understanding the relationship between two sentences, which is not directly captured by language modeling. In order to train a model that understands sentence relationships, we pre-train for a binarized next sentence prediction task that can be trivially generated from any monolingual corpus. Specifically, when choosing the sentences A and B for each pre-training example, 50% of the time B is the actual next sentence that follows A and is labeled as is next, and 50% of the time it is a random sentence from the corpus labeled as not next. So we could better understand this with this example right here. We have the man went to, let's we max this to max star. We have the separation. Then he bought a gallon mask milk. The label here is next because this follows this, or this is what comes next after this sentence right here. Now we'll look at this as an example. We have the man max to the star. Yeah, what we'll do now is we'll pick out a sentence at random from our data set, and then what we obtain is the man next to the star, and then the next is given as penguin mask a flight, less birds. So yeah, we have to label this, or the label this is not next. And as you could see right here, we have the outputs for the two tags. For the next sentence prediction, we're saying whether the second sentence is not next or not. And for the mask language model predictions, we're trying to predict the tokens which were masked from the input right here. Now the pre-training procedure largely follows the existing literature on language model pre-training. For the pre-training corpus, the authors use the books corpus, which is made of 800 million words, and the English Wikipedia made of 2,500 million words. For Wikipedia, we extract only the text passages and ignore lists, tables, and headers. And it is critical to use a document level corpus rather than a shuffled sentence level corpus such as the billion word benchmark, so that we could extract long contiguous sequences.